Good afternoon, class. This is the foundation for college algebra or the prerequisite. So let's refresh everybody's memory about what we are supposed to know. Natural numbers or counting numbers or positive integers. 1, 2, 3, 4 to infinity. Whole numbers, we just added 0. Integers, we go on the left side, we include the negative numbers. So 0, 1, 2, 3 to infinity, -1, -2, -3 to infinity. Rational number. Any real number that can be expressed in the form of a over b, where both a and b are integers. So in other words, a fractional format. So if you happen to have any of these numbers that were mentioned before, they're all rational numbers. Also, if you have a decimal that is either repeating or terminating, is also a rational number. Other than that, it's an irrational number, such as square root of 2, cube root of 4, pi, and when we put these two together, the union of the events give us a set of numbers such as real numbers. So, for example, if we happen to have 2.1, it's 2 and 1 over 10. So that is also a rational number. If you happen to have 0.3 bar, that is also a rational number because we can represent it with 1/3. Absolute value is basically distance from 0. A given number's distance from 0 on a number line. Therefore, the absolute value of every real number is either positive or 0. The only number whose absolute value is 0 is 0. The rest of them are all positive. For example, if you're looking at 5 or -5, makes no difference. Both of them have the same distance from 0. Therefore, absolute value of 5 is 5. So is the absolute value of -5. Again, we are looking at the synopsis of what we should know to move on with this course. So I'm going over this prereq, if you will. These are the exponential rules. So let's quickly go over the whole thing. A to the power of 0 is 1. A to the power of m times a to the power of n. This is called the product rule. We add up the exponents, a to the power of m plus n. A to the power of m to the power of n is a to the power of m times n. This is the power rule. This is also a form of power rule. If you are raising ab to the power of m, you raise individually. This is the quotient rule. A to the power of m over a to the power of n is a to the power of m minus n. And if you have a fraction to the power, you do them individually. And this is a negative exponential. There are a couple of them. For example, this one is 1 over a to the power of n. This one, negative n, comes up. And if you have a over b to the power of negative, you flip it over and you make it positive. For example, if you're dealing with those two, we just add 4 and 7. If we are multiplying those, we multiply 6 and 9 and 2. We multiply the numbers. 6 times 9, 54 times 2 is 108. Then z, we add up 5, 3, and 2. So 108 z to the power of 10. Anything to the power of 0, we said is 0. So this is 0, is 1. This is 1. This is 1. But what happens to this one? This is -1, and I want to make sure everybody understands why. Because of the order of operations. This one is done first, which becomes 1, and then the negative applies. That's why You want to be careful with that, okay? So one of the mistakes that students do is that they can't distinguish between these two. The left side is always negative x squared. My apologies, positive, my apologies. Whereas the left side is always negative because of the order of operations. So two different things, we don't want to mix them up. A couple more examples quickly. So we discussed the power rule. If you look at this example, 5 to the power of 3 to the power of 2, this is 5 to the power of 6. This one, the order of animation is not correct. Let me actually fix that. Sorry, guys. So this one is 5 to the power of 6. Let me get the laser point. This one, 3 to the power of 4 times 3, which is 12, x to the power of 2 times 3, which is 6. And you have to write all those steps, not necessarily, but just to let you know. For this one, 2 to the power of, we multiply these two, 15, and b to the power of, we multiply these two, 12. Dealing with polynomials and the concept of a like term. Like terms are terms with the same variable raised to the same power. This is an example. They all have the same variable. In other words, this part identical. So what's the difference? This is the coefficient, negative 13, the coefficient 4, the coefficient negative 1. What is the definition of a polynomial?
We can answer.
I'm sorry?
We can answer, or
Oh, you want to answer the bottom? Of course, of course. But before you do that, a polynomial is a term of a finite sum of terms with only non-negative integers exponents permitted on the variables. So that is the definition you want to pay attention to. Now we want to add these two. Yes, go ahead, please. Sharon, did you want to add them up? Is that what you wanted to do?
I wasn't sure if you were asking a question or not.
No, I wasn't, but you're more than welcome to, add them up. So what do we get? If you wanted to do that, it is absolutely up to you. In any event,
Let me try.
yes, go ahead. We add these two. We add these two. Finally, we add those two. Okay.
Negative 10x to the third power. Or those
Okay.
ones at the
So
bottom.
I see what you mean. I see what you've done. You added this, okay. You are absolutely correct. I wasn't asking for them to be added, but that's absolutely fine. Thank you for doing that. It's perfect. It's absolutely perfect.
Oh, okay.
No word. It's excellent. All right. I was showing the bottom. We had we had 2y to the power of 4 minus 3y squared plus y. And we wanted to add it to 4y to the power of 4 plus 7y squared plus 6y. To add those, we were adding like terms, like 2y to the power of 4 and 4y to the power of 4 gives us 6y to the power of 4. Negative 3y squared, positive 7y squared, they add up to 4y squared. Y and 6y, 7y. All right. Everybody knows how to multiply. There is something called foiling. F stands for the firsts, outers, inners, lasts. So with that being the case, it means the following. So first we multiply these two. Then we multiply these two. So first we get 6m times 4m, or 24m squared. Then we get 6m times negative 3, which gives us negative 18m. Then we multiply these two, gives us plus 4m. Then we multiply these two, we get negative 3. That's how we do this. All right, and these are some special products. We multiply conjugates. X plus y, x minus y are considered conjugates. We get x squared minus y squared. When we raise this to the power of 2, we get x squared plus 2xy plus y squared. When we raise this one to the power of 2, we get x squared minus 2xy plus y squared. These two are called perfect square trinomials. The next thing we want to spend a couple of minutes on, let's do some factoring. So to do the factoring, we take a common factor out. So the very first step is to take the GCF, which stands for the greatest common factor. And as we can see, y squared is in common. We take it out. You don't have to show it like this. You can go just right to the answer. Y squared times 9y cubed plus 1. Needless to say, you should always look at the final result, see if there's anything else you can do. The next one, we notice we have 4 terms, and the process of dealing with 4 terms. Anybody remembers how we factor when we have 4 terms? What is the process called? Anybody? All right. When we have 4 terms, when we have more than 3 terms, we call it factor by grouping. So somehow the group should work. For example, we group these two and we group these two. We want to find a common factor. It may or may not work. If it doesn't work, then we go with the first and the third. Then we go with the first and fourth, until it works. And if it doesn't, there is nothing in common. Needless to say, as always, the very first step is taking the GCF out. So if we put the first two together, is there anything in common for the first two?
They have the variable m in common.
Beautiful. And the last two, anything in common, class?
Just number 3.
Perfect. And that's all there is to it. So we take out m from the first two, 3 from the last two, and notice this is identical to this. So you write it right here. And then whatever is left from the other one, positive m and positive 3. That's how you do the factor. This is by grouping. So what is the process of factoring? Let's quickly recap that. A general review of factoring, everybody. The very first step is to take the GCF out. Then we consider the number of terms. If you have 4 terms, we do it by grouping. We have 3 terms. If you have a perfect square trinomial, we factor them accordingly. If it's not a perfect square trinomial, and we have x squared plus bx plus c, we want 2 numbers. The sum is b, and the product is c. If it's ax squared plus bx plus c and a is not equal to 1, we use trial and error, or we find 2 factors of ac whose sum is b, write these factors as coefficients of 2 like terms that when combined equal bx, and then factor by grouping. We're going to discuss this again, and I hope this is just a reminder and it's coming back to us. A difference of squares. And we have 2 terms, a squared minus b squared is a plus b times a minus b. Sum of cubes, a cubed plus b cubed is a plus b times a squared minus ab plus b squared. A difference of cubes, a cubed minus b cubed is a minus b times a squared plus ab plus b squared. I hope everybody remembers this stuff. If not, later on you want to go over this recording. Hopefully most of this stuff is going to come back to you. Okay, I seem to have a problem in my end. Something has happened, everybody, so just hang in there. All right, so that's the synopsis of factoring. Again, refreshing everyone's memory as far as some perfect square trinomials, difference of squares. So we want to do the factoring in these 2 cases. I hope you recognize what's going on. This is a perfect square of 4p. This, let me just show you that because this is important. So this is 4p quantity squared. This one is 5q quantity squared. Now, what about this one? If the multiplication of 4p and 5q times 2 is there, this is the case. If it's negative of that, this is the case. As you can see, we have negative of that, since this is minus, we have this one, which means 4p minus 5q quantity squared. The next one, this is the perfect square of 13x. This is the perfect square of 4y squared. If I multiply these two and multiply it by 2, let's see what happens. I get 104xy squared. And because this is a positive sign, I'm going to use this one. X plus y quantity squared, that means 13x plus 4y squared quantity squared. We should recognize. We go to the next one. We should recognize this is 2m to the second power minus 3 squared. In other words, you need a parenthesis here. So let me put that here because that's important. Otherwise, it's not correct. And so it's 2m plus 3 times 2m minus 3. Difference and sum of cubes were discussed. So if we have this one, we notice is x cubed plus 3q. This is the pattern. So replace the x with x and y with 3. When you do that, pay attention that this would be your final answer. Okay, I hope it's pretty straightforward. Let's look at rational expressions. Rational expressions are in the form of a over b. Where a and b are both polynomials. And so we always have to put them in the lowest term. To do that, we always do the factoring if there is anything in common. We can factor this as 2p minus 1 times p plus 4. The bottom is very clear, 5p is in common. And by the way, the top is really not too bad because 2 is a prime number. And you can come up with the answer. Now 2p squared plus 7p minus 4. You'll see the factoring in case you forgot. There are different methodologies, and I will go over all the methodologies of factoring later on. I'm going to remind you. For now, I'm going to just show you that it gets factored out, and you want to remember some basic factoring and do the job. Again, I will go over more details as far as factoring is concerned. When we multiply and divide fractions or fractional expressions, we multiply the tops, we multiply the bottoms. That's how we do it. For the division, we flip it over. And so let's take a look at this example. Now, you can go through the process, or right here you do the simplification. So I'm going to go through the process, but as a college algebra student, you don't have to write all of these steps because you've had some experience with algebra. So to do that, you can write it as follows. The numbers are 2 and 27. You write the 27 as 9 and 3. The bottom is 9 and 8. You can write the 8 as 2 and 4. We have y squared here. So you can write y squared and y cubed. The reason you do it this way, so you can cancel this 2. You can cancel this 2. You can cancel this 2. Let me do that. So 2 and 2, 9 and 9. You cancel it. And whatever is left is the answer. However, you really don't have to do this right here. You should work on it and be able to get to this answer. It is ultimately up to you, but it's really not too bad. How about division? The very first thing is to change this to a multiplication by flipping it over. And factoring everything. Again, I'm not going to dwell on factoring too much. You can see that later on, but the factored form of each expression is a must. And again, this is a prime number, so it's not too bad. You can always do the trial and error, and that's p plus 4 times 3p minus 1. But the rest of them, you just take a common factor, okay? So over here, you take out 8p squared. Over here, you take out 9. Over here, you take out 12p cubed. So you do that, and now the division becomes a multiplication by bringing this up and this down. So again, let me put a red mark next to it. This will flip this over such that this goes down, this goes up. Now, as you can see, certain things cancel each other. For example, p plus 4 cancels out p plus 4. 3p minus 1 cancels out 3p minus 1. We have 12p cubed at top and 9 times 8p squared. Let's write them so it doesn't get confusing. This p cubed that cancels out this p squared, and it gives us p. I hope you realize this is 72, which is divisible by 12 and gives you 6. And that's how you get to this final answer. All right, class. Again, reminding you of some of this stuff that you've seen, you've done, you should be pretty comfortable with. And you're more than welcome to stop me anytime. Again, we will see the whole thing again with some of them with more details, but there's really nothing brand new here. You've had all of them in previous courses. You add fractions only when you have a common denominator, okay? The same thing for the subtraction. So if I want to add these two, and remember, subtraction is a form of addition. The very first thing I need to factor every denominator. So this one I need to factor y times y minus 1. This one I need to factor. The very first thing I want to show you that the very first step. 2 comes out. Y squared minus 2y plus 1. And that's a perfect square trinomial of y minus 1 squared. So what is the LCD? 2 times y minus 1 squared. I hope you see that. So let me write this for you. 2y minus 1 squared. So when that is the case, compare this one to this one. You see 2 is missing times y minus 1. So you have to multiply this by 2 times y minus 1, the top and the bottom. And you compare this one to this, the only thing missing is y. You multiply the top by y, the bottom by y. And now you really have one common denominator. You don't have to write two common denominators, okay? One is good enough. But both of them give you the same thing here. And then if you multiply these two, you get 2 times y squared plus y minus 2. And you can add them up. 2y squared plus 2y minus 4 minus 3y squared. Is to add up to negative y squared. So it's extremely important to be able to write this properly, okay? And by the way, this is a prime polynomial. That means it can't be factored out, okay? So we're taking a common denominator. Sort of too many steps here, but it's really not too bad. Simplify complex fraction. Complex fraction is fraction within a fraction. So you can multiply the top and the bottom by LCD, which is a times a plus 1. There are 4 fractions, and the LCD is a times a plus 1. Now, the next step shows step by step how you redo this. But I just wanted to show you, but I wouldn't do that. So right here, I'm going to multiply these two. When I multiply by this one, a plus 1 goes away. So let me show you what I would do just in case, if I wanted to show you that. When you multiply this one by this, a plus 1 goes away, and you get a squared. When you multiply this one by this one, a goes away, and you get 1 times a plus 1. When you multiply this one by this one, a goes away, get 1 times a plus 1. Multiply this one, a plus 1 goes away, becomes 1 times a. However, it's showing you all those steps here. I wouldn't really waste time here. In other words, from here, you go here, and all you have to do is simplify the top and the bottom by putting them together. Complex fraction. Exponents, we've already discussed that. Just to see a negative exponential, a to the power minus n is 1 over a to the power of n. So I have shown you this one, and I would use this one as 5 halves to the power of positive 3, which is 125 over a to 5 cube with the over 2 cube. Or you can write too many steps for it. I wouldn't waste my time writing too many steps. Okay, class? A to the power of m over n is a to the power of 1 over n to the power of m. So there are different ways of writing them. If you happen to have the nth root of a to the power of m, you can write it in this fashion also, okay? The relationship between rational exponent and radicals. So if we have this one, it means basically if I'm working on this, I'm going to write cube root of 125 and then square it. Cube root of 125 is 5 and square it is 25. I wouldn't go through this process, okay? But understand when we write 125 to the power of 1/3, it means the cube root, okay? That's the meaning. And this one, we just add up like terms. I hope you realize one easy way in one shot, you can say 27 to the power of 1/3 plus 5/3 minus 3. Why? Because 27 cubed is in the denominator. So that's 1/3 and 5/3 is 6/3 or 2. So 27 to the power of -1, which is 1 over 27. This is the way I would do that, just fast. But you can do this by putting the top together and then the bottom and then 1 over 27. It is absolutely up to you, makes no difference. It's a pretty simple process. The only thing I want to just add, because the parentheses was missing there, so let me just quickly put that.
I have a question.
Of course, go ahead.
You know how you subtracted 3 on the slide?
Yeah, let me, okay.
Even though it was
Because
the denominator? I don't understand why.
because it's in the denominator. A to the power of m over a to the power of n is a to the power of m minus n. And since this is in the denominator, I subtract the exponent.
Okay, let me
This
get a
is
screenshot.
this,
Thank you.
this is short. This is the quotient rule. This is the quotient rule. And right here in one shot, you could say 27 to the power of 1/3. Then you add 5/3 because they are being multiplied by each other at top. And then minus, let me use a different color. Minus 3 because 3 is in the denominator. Okay, this is known as the quotient rule.
The quotient? Oh, quotient. Okay.
The quotient rule. Okay.
Okay, let me get a screenshot. Thank you.
Sure. This will be recorded. You don't have to do that, Sharon. This is being recorded and will be available to you. But in any event, go ahead.
Oh, okay.
All right. Let's move on. We want to take the 4th root of 16. There's a number, you raise it to the power of 4, you get 16. The answer is 2. If you want to go through the process, I mean, you really should know the answer is 2. But you want to go through the process, you can say 16 to the power of 1/4 or 2 to the power of 4 to the power of 1/4, and the product of these two is 1. But, 4th root of 16 is 2. There is a number. This means there is some number to the power of 4, which is 16. So 2 to the power. If you look at this one, you would say there is some number to the power of 5 is negative 32. The answer is negative 2. Some of you may know 2 to the 5th is 32. Negative 2 to the 5th is negative 32. So the answer is negative 2. You can go through the process, or it's one of those easy numbers that perhaps we know. Eight to the power of 2/3. I have explained about this before. So 8 to the power of 2/3 means cube root of 8, which is 2 to the power of 2. And that makes it 4. Negative 32 to the power of 4/5 means the 5th root of negative 32 to the power of 4. We've discussed that this is negative 2. When you take negative 2 and raise it to the power of 4, because 4 is an even number, gives you positive 16. And again, we don't want to mix up these two. This is not the same as this. Okay? The left side is negative 16. The right is positive 16 because of the order of operations. All right. If you happen to have the same exponent and the same index, this is called index, then A comes out. And it depends whether n is even or odd. If it's even and you have any doubts, you go with absolute value. If you are known that the variables are positive, you don't need an absolute value. If it's odd, you have nothing to worry about. So we want the 4th root of p to the power of 4. That is the absolute value of p, because p could be positive, p could be negative. We don't know anything about that. The next one, I hope you know that basically you bring this out as 4, you bring this one as m to the power of 4, you bring this one as r cubed. Again, since we don't know they are positive or negative, you can put the whole thing in an absolute value, but sometimes they just put this one in absolute value. And here's the reason, everybody. Here's the reason. If you put it like this, it's fine. If you put it like this, it's fine. Why is it that we can't do it this way? 4, we know it to be positive. M to the power of 4, we know it to be positive. Why is that? Because 4 is an even exponent. So regardless of what m is, m to the power of 4 is positive. But this makes a difference. R cubed, because this is odd, we don't know if it's positive or not. So we have to keep it in an absolute value. So as far as I'm concerned, this is correct, and understand why this is correct. Now, here's the interesting thing. If we don't pay attention to this, we may think these two are the same, the index and the exponent. Therefore, this is negative 2. But that's not the case. It's equal to the absolute value of that. Why is that? Because the index is even. Pay attention to the fact that the index is even. Absolute value of negative 2, which makes it positive 2. Why is that? Order of operations. Let me show you. Order of operations. This one is the sixth root. First, you raise this to the power of 6. Makes it positive 64. The sixth root of positive 64 is positive 2. Okay, and that's extremely important to pay attention to. Now, what I want to show you is this. What if we are dealing with an odd index? Take a look. Cube root of 8 is 2. Cube root of negative 8 is negative 2, meaning if you're dealing with an odd index, the sign just comes out. Okay? Why? Because negative 2 to the third power is negative 8. Okay? All right, if we have the nth root of A, the nth root of B, when we multiply, we can multiply together. If we are dividing, the same thing. And if we are writing them in this format, we can multiply these two. Okay, I want to quickly explain the last one. You don't come across it often, but for example, if it's the third root of the square root of, let's say, 5, means the sixth root of 5, because when we don't write the index, the index is 2. All right, so this one, we multiply the 2, and we come up with 324, and the answer is 18. I'm going to show you a different method, because when the numbers get larger, it may be difficult to see the answer. So what you can do is, let's write it here. 6, you write it right here. 6, you write it as 2 times 3. 54, okay? You can write it as 2 times 3 cubed. I'm assuming 54 is 2 times 27, 27 is 3 cubed. So I can rewrite the whole thing as 2 squared, 3 to the power of 4. I'm going to divide the exponent by the index. Remember, the index, when you don't write the index is what? 2. So this comes out as 2. This comes out as 3 squared. 2 times 9 is 18. So this is really an easy way to come up with the answer. The next one is cube root of m, cube root of m squared. If you put them together, is cube root of m cubed, and it comes out as m. The last one, if we separate the top from the bottom comes out as 8. This is 8, so it makes life easy. We have just a few more pages to go. It's the square root of 175. I hope you realize is the product of 25 times 7, or you can say 5 squared times 7. I'm assuming everybody is okay with the factoring. So if you factor 175, can I divide it by 2? No. Can I divide it by 3? 8 and 5, 13. No. So you divide it by 5. And you get 35. 5 again, you get 7. You get 7. And this gives you that. So 5 comes out, 7 remains. So right from here, you can write this. All right, I'm going to show you what you probably see in most texts, and I'm going to show you my way for the next example. So they write 81 as 27 times 3, and then 27 comes out. X to the power of 5, they write it as x cubed times x2, x cubed comes out. Y to the power of 6 comes out. Z to the power of 6 comes out. Here's the answer. What I want to show you, I'm going to look at the same question that I believe I know how, and it's easier. So take a look at this in this manner. I'm going to write 81 as 3 to the power of 4. X to the power of 5. Y to the power of 7. Z to the power of 6. And I'm interested in cube root. Now, the method that I'm going to show you, it works faster and easier the more complicated the question becomes. You divide the exponent by the index. So if I divide 4 by 3, it gives me 1 with the remainder 1. So x to the power of 1 comes out. X to the power of 1 remainder. X to the power of remainder 1 remains. This one, 5 divided by 3 is 1 with the remainder 2. So my apologies, this is x, everybody. Let me. This should be 3, this should be 3, and now we're going to go to x. So x to the power of 1 comes out, x to the power of 2 remains. Y to the power of 7. I'm going to divide 7 by 3, gives me 2, remainder 1. So y to the power of 2 comes out, y to the power of 1 remains in. Finally, use a different color. Z to the power of 6. If I divide 6 by 3, I get 2 with no remainder. Z squared comes out. This is the final answer. The more complicated the question, the faster this way, trust me. Okay. All right, let's look at a couple more examples of this concept. We want to combine them. We want to see if there's any way to come up with the same, radical format. 18 is 9 times 2. 9 comes out as 3. 72 is 36 times 2, and it comes out as 6. So I hope you realize this remains, okay? And this one is 9 times 2. This one is 36 times 2, or you can do the factor. So this is 7 squared of 2. This is minus 24 squared of 2. This is 24 squared of 2. And so you add 7 minus 24 plus 24. You add this number, and this number times square root of 2. For the next one, you may see that 98 is 49 times 2 or not, or you can do the factoring. The reason I say 49 because 49 comes out as 7, and 32 is 16 times 2. You can see that. So if we do that, this number will come out as 7. This will come out, or you can divide by the exponent. 2. 16 comes out as 4. So this one becomes this. And this one becomes this. To combine them, you have 7x and 12x in front times 2xy. Notice those parts are identical. This is identical to this. So all you have to do, combine 7 and 12. So that's how you do that. You can combine the two. Spend a little bit of more time on roots because in the past I've noticed students have a little bit of a problem with that. And of course, we're going to come across it again in college algebra, but it's not a bad idea to see how things go. Here's the next one. We do the foiling, multiply these two, multiply these two. So square root of 2 times square root of 8, square root of 2 times -5, multiply these two, multiply these two. This is foiling. And so becomes very simple. The first one is the square root of 16, which is 4. The next one is -5 square root of 2. The next one is 3 square root of 8, where 8 is 4 times 2 comes out as 2, and 2 remains, -3 times 15. And we can combine these two. Also, we can combine these two. So we get -11 plus square root of 2. Now, I hope you remember a minus b times a plus b was a squared minus b squared. This is the fastest way to do that. So you square the first one, you square the last one, becomes 7 minus 10 or -3. Square the first one, minus square the last one. So I hope everybody's clear. We have one more page to go. All right, we want to rationalize the denominators. And the process is, for this one, we want to get rid of the radical. So we multiply by square root of 2 and we divide by it. Everybody knows this is equal to 1, so this is justified. The two of them give you 3 at the bottom, and the top is 4 square root of 3, and we are done. What do we do here? Remember what we want. We wanted this to come out, so we want x to come out. But if it's a cube root, and we have x to the power of 1 inside, we need to multiply it by cube root of x to the power of 2. And that's really the key. You are going to multiply by cube root of x squared, the top and the bottom. So you're going to multiply by cube root of x squared, and the bottom comes out as x. Okay. I'm not going to do this, but I'm going to show you something. If I have, let's say, 5 over, I don't know, 7th root of x cubed, what do you need it to multiply it by? I want you to see that. So you put the 7th root, you put the 7th root, and you look at this exponent and you say, what is the index minus the exponent? 4, so you need x to the power of 4. Because now the product of these two is 7th root of x to the power of 7, which is x. All right, so that's the reason. Finally, what if we have a couple of terms in the denominator? We multiply by the conjugate of 1 minus square root of 2, and we divide by it. In other words, we are going to multiply by 1 plus square root of 2 and over 1 plus square root of 2. So what happens is that this one becomes 1 squared minus square root of 2 squared, which is 1 minus 2. And obviously 1 minus 2 is negative 1, and it changes the sign in the numerator. Everything turns into negative, so becomes negative 1 minus square root of 2.